So today I thought we would begin with a nice leisurely investigation of the parsimonious lambda calculus. I found a paper that is companion to the Church Meets Cook and Levin paper, which I think has a slightly friendlier syntax and shows some of the intuitions of the syntax. So I will screen share and go over that. I think Tomislav, you will be pleasantly surprised by one of the primitive constructs.
Oh yeah, I'm already surprised.
All right, so let me go ahead and do a screen share. And here we go. So this is the simply typed parsimonious lambda calculus. We can just look at the terms as, just to get our eyes accustomed to the notation a little bit. And then we can look at the types. So essentially, there's an affine version of the lambda calculus sitting over here. What that means is that you have affine variables which can be used once or not at all. So at most once. So you have an affine mention, you have an affine abstraction, and you have an affine application. So that's the affine part. And then you have an exponential part. And this is intriguing because it uses a portion of the multiplicative, the intuitionistic multiplicative linear logic. So just to be clear, so we're making an assumption that u, the term u in this let expression, evaluates to a tensor. So you can form tensors here. So u evaluates to a tensor, and that tensor will be bound to the a and the b. So you'll have a t and some v over here, or a v and a w over here, which will be here, and the v will go to the a, and the w will go to the b in t. So you can think about it as like a kind of unpacking of a tuple. It's not quite the same, but roughly speaking. You have exponential variable mentions, but they must always be indexed. So in general, what's going to happen is that exponentials will stand for streams, right? So that these things are going to be streams. So here's a finite list, and a stream is going to have some finite prefix, after which you have some bang in front of it. And we'll see that down here. And then so this let bang x is going to give you a bunch of indexed x's. So x0, x1, blah, blah, blah. And they're going to take positions according to some rules inside T. So again, T is going to evaluate typically to some stream, where a stream is going to be a finite prefix in front of a banged term, and then these x's are going to stand for indexed variables inside that string. Hopefully that's clear. Does that make sense? Does anybody have any questions about the syntax?
This tensor is this connection to
think about it like in Scala, where you say, var open paren x comma y close paren equals some term t.
Oh, I see.
Right? So that will pick out the, so t has got to evaluate to a tuple, and then you pick out the left and the right.
Understand, yeah.
Cool.
And the affine what affine means is this is
Affine
very
means
similar to linear, or
at most months. So it's like linear, but you can erase.
Mhm. Okay.
So you can't duplicate, but you can erase. Okay, now there's an extra condition on the exponential parts. All right, so every term that is, bounded by a bang, right? So we've got some term t, and we form a new term by putting a bang on it. That's called a box. So these are boxes. And there's a parsimony constraint, right? So the parsimony is that every exponential variable, xi, appears in at most one box, okay? And at most, um, uh, um, um, and if you have double boxes, it appears in at most one therein. And the index of such an occurrence is the maximum in the term. Okay, so let's give some examples. So lambda a dot let bang x equal a in x0 bang x1 is parsimonious. Does that make sense? So x0 occurs, doesn't occur in a box, but x1 does occur in a box, and it's the maximum in the box. Just want to make sure that there aren't people trying to hop in the room. No, looks all good. Sometimes
what is the
yeah.
What is the relationship between x0, x1, and x? Are they?
So think of this as giving you an infinite list of variables. So x0 is going to be the first position, x1 is going to be the second position, x2 is going to be the third position.
Oh, so this let bang x is something like new in rholang. We are creating
not quite a new. This is real. If you take the bang away, it's just an ordinary let, right? Now, when you put the bang here, it's saying that this thing is a stream. So that this is a stream, and this is going to be, so x0 is going to, pick out the, it's a little more sophisticated than this, but roughly speaking, your intuitions are not terribly off. If x0 picks out the first position in the stream, x1 picks out the second position in the stream, and so on.
Okay, I see. So A is the stream, and
no, A is not a stream. Oh, sorry. Yes. A is a stream. Yes, over here.
And we are pulling from A as a stream. We are pulling out and we are saying, oh, now we have x0.
Yes.
And another value is x1.
Yes.
And this x1 will be in the box. And
yes.
I still not understand what is in the box, but yeah. Okay.
Yeah. Okay. So none of these are parsimonious. So this one's not parsimonious because x occurs in two boxes. This one's not parsimonious because x occurs in two boxes. This one is not parsimonious because x occurs twice in a box. It's only allowed to occur once in a box. And this one is not parsimonious because the index here is not the highest index in the term.
So all of these x's are considered as one variable.
Yeah. So again, x is a stream. X is a stream, and then the zeros give you the position in the stream. I mean, the indices give you the position in the stream. Okay, so there's a little bit more notation. So you can write t plus plus, where we replace every free occurrence of the exponential variable xi with xi plus 1. So it's a shift. We're shifting all the variables over. Notice if your term is parsimonious, the new term will be parsimonious. And then and now we can formalize our notions about streams. A box with a finite prefix in front of it is called a stream. Okay, and we'll write terms of this form in bold. And we introduce this notation here. So UI is just going to be ti plus 1 if I is less than n. So U0 will pick out T1, U1 will pick out T2, and so on, right? Now, when we get up to n, so UN is going to be U plus I minus n. So I is n now, so this is 0. So U plus 0 is plus plus applied 0 times. So plus j is this plus plus operation applied j times. So the plus plus operation is applied 0 times. So un is going to just be u. Un plus 1 is going to be u plus plus. Un plus 2 is going to be u plus plus 2. Right, and so on. So he writes it out down here. Does that make sense? So the bold term u is thought of this way. Does that make sense? So one way to think about it is that the box is giving you copies of the term where you've shifted the variables over.
So we are starting from T1 to Tn.
That's the finite prefix.
Mm-hmm.
So you have a finite so think about it like, rest arguments, right? So you have some finite list of arguments, and then you have a rest. But in this case, the rest is an infinite copy of this. Each one of these, remember, according to the parsimony rules, you can only mention x once, and it has to be the highest index in the whole term for this thing to be parsimonious. So when we apply the plus plus operation, we're making a copy of u where we get the next x, and then the next x, and then the next x. So this is allowing us to make copies of u with fresh versions of the variable. So in that sense, your intuitions about bang is somewhat similar to the pi calculus nu.
Mm-hmm.
Does that make sense?
Yes. And is this u referring to t, or this is like new, completely new variable?
This is some other term. U does not refer to some t. U is some other term.
Okay, okay.
So this is what it looks like. So you have some finite prefix of terms, then you have u and copies of u thereafter. So
okay,
then the evaluation is pretty much as you would expect. So we just went through the intuitions. So if we apply an affine abstraction to a term u, then we just get the body of the abstraction with u for a and t.
So this is basically the same as with normal lambda calculus.
This is just
But
like lambda
we have-
calculus. Yeah, it's just normal beta reduction. Okay, so now moving on, if we do let A cross B equal U cross V in T, then it does exactly what I said it does, right? So we put A in, we put U in for A and V in for B in T, right? So you can think of it like a pairing operator. And then here, as promised, U is a stream and X is going to be a set of positions into that stream. And we're going to basically substitute U in for X in T, right? So each UI is going to go for an XI in T. Does that make sense?
It's like a binding operation, or
That's correct. It's just like a normal let, right?
Mhm. Okay.
So if you translate the word var for the word let, this will be, you'll get the corresponding scala.
Mhm. Understand.
Okay. All right. Any other questions? Okay, the reason this is interesting, again, the reason we're studying this calculus is because we're going to see how this calculus allows us to encode circuits. So we're going to get an equivalent, a version of SAT that we can express directly in this calculus. So are people familiar with sort of traditional complexity theory?
I'm not really.
Okay, so we'll have to review the complexity theory. I'm not prepared to review that today. I can go over the stuff that is most salient with respect to the results that we're interested in. So I'll give a game plan. Next, Casper, what we'll do is we'll look at how to encode lambda calculus into row calculus. And we'll, if time permitting, we'll look at how the parsimonious lambda calculus goes into row calculus. Right, so then what we'll get is a path from SAT to row via parsimonious lambda calculus. Does that make sense?
Yeah, yeah.
Okay, so that's the idea. And so then we can port over all of the ZK machinery, because we have a path from ZK through SAT. So we go ZK, SAT, parsimonious, row. That's the idea. And so so what we're doing is we're putting together all of the pieces that we need. This is just an engineering operation. We're putting together all the libraries that we need in order to build ZK features in row. And essentially, the way we're doing that is this guy here, what's his name? Mazza, Damiano Mazza. He has put together all of the libraries needed to do SAT into the parsimonious lambda calculus. And we're just going to extend his results to take it over to rho. And then he just takes it as a part of ambient understanding that, zk goes through SAT. There's a lovely, I recommend to everyone, there's a lovely number file on zk knowledge, zero knowledge proofs, and SAT. So it's very, very plainly, simply described. And so that will help you pick up some background information. Let me see if I can find it, and I'll drop it in the chat. 1 second. Yeah, so sorry, I just now saw Steve's comment about parsimonious. So that's an older meaning. Typically we think of parsimony as economy, right? So, someone's use of language is parsimonious, meaning they have been very economical in their use of language. But this other meaning is also very appropriate for the cases that we're considering.
Okay, thank you. And the other word, SAT, I may have missed it. Is that an acronym, or what?
Yeah,
What is?
it's satisfiability.
Oh, okay.
It's a class of problems.
Okay.
Yeah, I'll go into that again. If you watch the number file video, that will start to fill in some of the gaps there.
And this will be to support privacy, but also to help us to not do the whole replay, right?
Not do the whole replay, right? That's the prime. So the privacy stuff is a freebie. The main aim is to not have to do replay.
So in terms of the privacy, Greg, what would be some of the applications? For example, for the COVID passport, we're thinking of doing encryption as the way of creating some degree of privacy. How would that change with the zk?
You could hide all the transactions that have to do with uploading personal information.
I see. So people won't necessarily know what you are keeping on the chain.
That's correct.
So that it'll help hide the metadata.
That's not, yeah. It'll help hide a bunch of forensic data.
Okay. I see.
Can we say that we are basically hiding the input and we are producing the result?
Yeah, that's another way of saying it. Yeah. Okay. All right. So let me go back to the paper, and we'll take a look at. So we've looked at some of the reductions. We'll finish off the reductions, then we'll look at the types, and then I'll stop and see if NutZipper wants to talk about his article. Give him some time here to talk about his article. Okay. So let me turn the screen share back on. Okay. So we've looked at these three, and these are really contextual reductions, right? So you have if you reduce inside, if you put T inside some context, and then apply to U, then that's the same as putting TU inside some context. So that's a little bit odd to me. Oh, I see. So he's making an assumption about the form of the context. So you have let Q equal V in the whole. Now these two make sense. So hopefully this will jive as you start using the calculus a little bit. All right, so moving on to the types. So he's presenting them in terms of introduction and elimination rules. So everything on the left is an an introduction, and everything on the right is an elimination, with the exception of the abs and coabs. So we'll have to take a look at that in just a minute. So you've got a gamma and a delta, and together with the typing that the affine variable A is of type A. So that's to the left of the turnstile. So these are your dependencies. And so if on the right, the mention of A, you get that the mention of A is of type A. So whatever these dependencies are over here, if we know that A is of type A, then we get to conclude that A is of type A. Right, so that's axiom, and you can think of axiom as a kind of wire, right? So if I had an A typed A, then I could produce an A of type A. Hopefully that's clear. This is the core of linear logic, that the variables are wires. Okay. And that's kind of how you get off the ground, right? So these could be empty, and this is the get off the ground thing. So now, given this type context here, where we have a dependency that A is of type A to conclude that T is of type B, then we can abstract away A, right? So we pull A off of here, move it over to the right, put it under an abstraction. And now the corresponding lambda term is a lollipop, right? So this is, in Scala, this is the arrow, but we denote it by a lollipop because we know that A is used at most once in T, whereas if this were the arrow type, right, then A could be used a lot in T. Does that make sense?
Yes.
Okay. And so the elimination of the lollipop is just, application, right? So I have that T is A lollipop B, and I have that U is of type A. So if I form the term TU, right, then I pick up these dependencies and these dependencies, so they're added together, and then I can form the application and get the B. So essentially, I'm feeding U into the abstraction that T is and getting the B. Okay, so that's pretty much standard. Over here, we're going to have the dual between forming tensors and picking them apart, right? So over here, we have that gamma delta gives you that T is of type A, and gamma prime delta prime give you that U is of type B. Then, piecing the gammas together and the deltas together. So he is providing, so there's some kind of separation between the gammas and the deltas, and I haven't figured out yet what that, why the discipline is the way it is. So I don't know why he's putting some kind of partition between the gammas and the deltas. So probably this is the affine environment and this is the exponential environment. That's my guess as to what's going on here. Um, so anyway, so we put the gammas together, we put the deltas together, and those dependencies give us that T tensor U is A tensor B. So we just form the pair, and so the pair is the pair of the types.
Is this a connection to intersection types?
Yes and no. I mean, we're not forming an intersection, right? We're forming a tensor, so the resources are not shared, right? That's the whole point of separating the gamma and the delta. And it's a kind of conjunction, so it's related to intersection types in that way, but it's not an intersection because, you know, we have a completely separate gamma and delta that's used to grant us that T is of type A, from the gamma prime and the delta prime that's used to grant us that U is of type B. So these resources are different from those resources. And when we combine the total resources, then we can get that the tensor is going to be of type A tensor B.
Okay.
Yeah. So in particular, if let's say that gamma prime and delta prime were exactly the same syntactically as gamma and delta, then you'd have two copies of the resources over here and two copies of the resources over here. So not intersection.
Oh, I see. Okay. Mm-hmm.
Okay, so then the flip side, suppose that gamma prime and delta prime are what's needed to infer that U is of type A tensor B. And suppose that gamma and delta and A is of type A and B is of type B are necessary to infer that T is of type C. Then we can take the we can take the so notice that these therefore are going to be affine variables, right? So then we combine the gammas and the deltas together. We form a let expression, which is going to pick U apart, and then in T we get C, and that lines up exactly with this reduction rule, right? So this is going to reduce to U for A and V for B and T. So since T was of type C, then this whole let is going to be of type C. And we're going to do a very analogous thing over here, right? So this introduces the bang and this pulls the bang apart. So it looks like we have an empty gamma. We don't have a gamma. Let's see. And then it looks like A is going to be a vector of types. Yeah, I think the bar means a vector. That's my, yeah, that seems reasonable. So A is some vector of types. And this is, so it looks like the delta is what's being used for the affine part, and the gamma is being used for the exponential part. So sorry if I got that backwards earlier.
So when you say vector, you mean A0 and 1 and 2? And...
Yeah, exactly. Yeah, yeah.
Mm-hmm.
Okay. Although I'm not sure what's going on here. I think that might be a typo. I think not an X0, but an X. Yeah, I think that must be the case. I can ask him. Okay, so anyway, so you have an empty gamma. A is a vector of affine types, so a vector of affine variables and types, and those are your dependencies to infer that T is of type A, capital A. Then you have some vector of X's are a vector of exponential types. You've gotten rid of you've got an empty delta, right? So no more deltas because you've moved them over to the other side. And so bang t is going to have the x's for the a's. So that's, I'm fairly certain that this is a typo. The x is for the a's in, and that is going to now bang a. So the flip side is,
this is an operation like putting inside the box.
yeah, we're
And
so the a's, these affine a's are so what this is doing is creating a bridge between affine variables and exponential variables, right? So I've got a bunch of affine variables that are mentioned in T, right? And now I'm going to go get some I'm going to get some exponential variables, and I'm going to replace them with the affine variables in T bang or bang T.
okay.
Just make sure I've got this substitute. Yeah, U for A. Yeah, so it's going to be X for A. Yeah, it's a bridge between the world of variables. And then over here, we're going to pick things apart, right? So it's going to flip around the other way. So I've got some gamma prime and delta prime, which are what I need to establish that U is of type bang A. And I've got, yes, this is clearly indicating that gamma is the exponential variable context. So that's the partition. All right, so then gamma is of type, so gamma and X of type A and some delta is what we need in order to establish that T is of type C. So then together, we combine the gammas, we combine the deltas, and that allows us to form the term let X equal U, right? So that's going to make sense, right? I've got a bang here, I've got a bang here. So let X equal U in T is going to be of type C, right? So that's the idea. And then over here, let's start over here. So gamma and delta give us that T is of type A. Gamma prime and delta prime give us that U is of type bang A. Oh, I see. Then we combine the gammas, we combine the deltas to get that I put T on top of U. So I push T onto the stream U, and I get that's of type A. So basically, it's a kind of absorption, right? We're absorbing this into the bang. You see what's happening? This is not a tensor bang A. It's just a bang A. And over here, this is going to be the dual of that. So let's see if we can pick this apart. I've got X is of type A. So I've got this type context gamma together with X of type A. I've got a type context delta with A is of type A. And these dependencies are what allow me to establish that T is of type C. Then we have, we can pull the gamma X down. Oh, maybe the X0 is not. I'll have to study that part a little bit more. I shift T over, right? So, and then I substitute X0 for A, and that gives us C. And that means that this whole term here is of type C. All right, so I'm going to have to study this one, these two a little bit more, but you know, we're not too far off in our understanding.
What is abs and coabs means?
I don't know what they're referring to, but it's a kind of absorption. It has to do with this. See, we can absorb the A tensor bang A into the bang A.
So we are basically pushing this on the stream and the moving first element from the stream.
Yeah.
In that sense.
Yeah. So that's you know, again, I just began studying this, so you know, I'm not completely completely familiar with everything here, but this is the, you know, a rough account of what's going on in the calculus. So next time we'll take a break from this calculus and just look at how to get lambda into rho. And then we can look at how to get, after we understand how that's done, then we can look at how to get the parsimonious lambda into rho. Right. So those are important steps. So I'll stop here and see if NotZipper wants to take some time to talk about his article.
And when we are not doing replay, we need to transfer the values that we need to update in the state. So basically this means that our event log must be extended with the values also, right?
Yes. Remember, we do have the state transition from the play, so we know what the new state should be. We just don't know if we trust it.
But we don't know. When we are doing replay, then we ends up with the values. We don't know this from the event log.
Okay, yeah, so we'll have to extend the event log for sure.
Yeah.
Okay, I'm here. Can you hear me?
Yes.
Yes, we can hear you.
Okay, I'm just so briefly wanna to say that please take a look at the article I posted as a series of tweets, and now I've pushed the PR to the rholang.io. I've prepared their well-formed article with the images, illustrations. So its first feedback is quite nice. It's about what's block merge. So people were asking what's block merge and why is that about scaling. So I was trying to answer in simple terms what's that and give a first analysis of implementation. So basically we have already
You're not sharing screen, NotZipper. I don't know if you meant to, but
yeah, no, I'm not. I'm on my phone. I actually don't have much to share.
Okay.
So article will be posted later. I've asked Toby to merge a PR. So just a brief introduction of what you should expect to see in this article. It's explanation of how our chain is different from other chains, at least what I'm aware of, and what's so special about the state transitions and how can we merge state transitions and why having a concurrent computational model is extremely important in this environment, which our chain has. And in the end, I have some preliminary results about the merging, which shows that for 10 and 20 nodes, time for preparing a merged state for a new state transition grows about linearly. I'll have more details in the following posts, and we're soon will have some out version of block merge, and hope folks will try to test that, maybe run their own charts and test that out. So that's it. Also, I want to congratulate Tomislav on joining and maybe being an active Twitter follower and create some articles and content there as well.
Yeah, I will try to be more active on Twitter.
Very good.
So that's it.
Very good.
Yeah,
No,
sounds good.
That's all good stuff. I really appreciate the work. I think the more people understand what it is we're doing, the more excited they will be about arching.
Indeed.
Yeah, and I very like the article that Anton wrote. It's very nice and very, very readable, and you know.
Excellent. So
Thank you.
you're waiting on Toby to merge?
Yes.
All right. I mean, you can also put it on the blog, the Archain blog.
Oh, sure. Well, it's
It'll become a Medium article.
okay.
Well, I mean, you can do all three. I mean, there's nothing wrong with putting it in multiple places and then maybe link from one to the other or something in some way.
Totally.
Well, actually, I think at least search engines will punish such content which posted in different places. So maybe it's not a good idea to just repost that word by word. So I will make something for our team blog.
Okay, cool. All right. Well, thanks to everyone. Appreciate your time and attention. And I will see many of you in about 15 minutes in the Dev Stand-Up.
Thanks, Greg.
Yeah.
See you.
All right.
Thank
Thank you. See you later.